Good morning. All right. So we started looking at some logarithmic functions yesterday. So we're going to continue with that, and maybe we'll get into the next section, which is some laws for logarithms. We'll kind of see how far we get. I did move the homework to Tuesday of next week. So the one that was due tonight, we're not going to get through the two sections that I need to before tonight. So I did go ahead and move that to Tuesday. That's because Friday and Monday are holidays, so we are not going to meet those 2 days. So Tuesday was the first class day that I thought would be sufficient for that. So again, don't forget, no meeting on Friday or Monday. I will not be here live. I'm still going to be working on Friday for sure, though. I do have meetings and stuff scheduled that day, so feel free to send me questions if you want to set up office hours that day or anything. I am available for that, and I have some advising appointments that day already. So just know I am working Friday, but there will be no class. Okay. Any questions about anything right now? And you may have gotten a grade from me for your test already. I started grading this morning. I'm about halfway through, so half of you probably have a grade and half of you probably do not. But I'm hoping to get those done by this afternoon. That's my goal. Okay. All right. Well, let's go ahead and jump back into section 4.3, sorry. So we're going to look at some transformations of our logarithmic functions now. So the first thing we want to think about is, what does the original parent function look like, right? And that's what we looked at yesterday. And then we'll start applying some of the transformation rules that we already know, right? So what would be our parent function for this g of x graph right here? Okay, good. So it's going to be the base 2 log of x, right? And I know that's hard to type in the chat. Okay, so in this case, whatever the base is of this one, right, we want to keep that same base for our parent function, and then the transformation is going to be based off this negative out here. Well, base 2 log of x, that's the graph that we actually looked at yesterday. And so what are some of the key things that we've noticed about that graph when we looked at it yesterday? So are there any points I could put on that graph? Are there any asymptotes I could put there? So 0 and negative numbers are undefined, right? So there's not going to be anything from the y-axis and to the left, right? Everything on our graph is going to be to the right. What else do we know about our graph? Do we have any asymptotes? There's a vertical asymptote at 0, right? So vertical asymptote at x equals 0, so we know that. Do we have any points on our graph that we know for sure? Any intercepts? Let's go with that. So anywhere where it's going to cross an axis. Okay, good. And in this case, it's going to cross the x-axis at 1, right? So we're going to have a point here at 1, 0. And then remember the basic shape this time, right? It's going to go up and to the right. So we have this vertical asymptote at x equals 0. It's going to curve up and to the right. It's going to go through the point 1, 0. And it's just going to continue up and to the right like that. Okay, so that's the basic shape that we're looking at for our logarithmic function now. Now, again, it really doesn't matter what that base is. That's still going to be the basic shape. You're still going to have your vertical asymptote. You're still going to go to the 0.10. The only difference this number right here makes is how steep or shallow this curve is, right? So the bigger that number, okay, the faster it's going to grow out this way. The smaller that number, the more it's going to go up as it goes out to the right. Okay, that's the only thing that's going to change there. So now let's look at this, right? So what's that negative going to do to our function? Good, right? So this is going to give us a reflection over the x-axis. Okay, so just remember, if you have a negative, that's a reflection. If it's out front of the function, that's over the x-axis. So if I take this graph here now, and I reflect it over the x-axis, think about what that's going to look like, right? So are there any points that I can put on that graph automatically? Yeah, 1, 0 is still going to be on that graph, right? So I'm still going to have my point, my x-intercept at 1, 0, because even reflecting this, right, that's not going to change anything if I reflect it over the x-axis. Do I have any asymptotes for that graph? Okay, so y equals 0 would be a horizontal asymptote, right? That would be an asymptote along this axis. So it actually is going to be a vertical asymptote still at x equals 0. Now the difference here is because we're reflecting it over the x-axis, instead of approaching our y-axis here at x equals 0, it's going to be going up this way because this piece is going to get reflected up here. So now this is going to be going that direction, and then it's just going to curve down and to the right like this. Okay. So again, this piece down here gets reflected up here. That gives us this piece up here. And then this piece that's going like this is going to get reflected down here. And so that's what gives us this piece right here. But again, the x-intercept does not change. Asymptote does not change. We're just approaching that asymptote in the opposite direction now. Now, let's talk about domain and range because we've got our asymptote here. So what's the domain of that function? Good, right? So 0 to infinity. We don't include the 0 because there is an asymptote there. But all of our values here have to be positive, right? And x, so 0 to infinity. What's the range going to be for this function? Good, right? So this thing's going to go all the way up to positive infinity, and even as it curves down this way, right, it's going to continue down to negative infinity. So we're going from negative infinity to positive infinity, right? All values for the y. Any question, any of those pieces now? Why is it 0? Are we talking about domain or vertical asymptote? Give me a little bit more there, Kenneth. The domain, okay, so in this case, the domain, right, we're thinking about all the possible x values. So we're thinking about this graph right here. And notice there's nothing in the negatives, right? Just like you told me before at the beginning, right? We're not going to have anything less than 0. All of our x values are bigger than 0 here, and they're never going to hit x equals 0 because that would be the y-axis, and that's where we have that vertical asymptote. So we're starting from 0. We're going all the way to infinity. This includes all the positive values, not including 0, because there is an asymptote at x equals 0. Does that answer your question? Okay. Any other questions there? All right, let's look at the second one here. So what are we going to have this time? What type of transformation? Okay, good. So this time it's going to be a reflection again, but because the negative is inside, it's going to be a reflection over the y-axis instead. So now let's think about that graph. Again, we're going back to the original parent function. So if we were to take the original parent function and reflect it over the y-axis, right? Let's think about some of our key points on this graph. Do we have any intercepts that we can put on our graph? Good. So this point here at 1, 0 gets reflected over the y-axis, so it's going to be over here at negative 1, 0 instead. Now we have an x-intercept at negative 1, 0. What about our asymptotes this time? Okay, so again, right, y equals 0 would be a horizontal asymptote. So if we want the vertical asymptote, it's actually going to be what? Good. It's x equals, right? So we still have a vertical asymptote at x equals 0, because even if I reflect this curve over the y-axis now, all of this stuff just gets flipped over, but I'm still going to be approaching this axis, right, at x equals 0, just from the other side now. So what my graph is going to do is it's going to curve down this way. It's going to go up and to the left on this side now. Right? Any questions on the graph now? All right, let's talk about domain and range. So looking at that new graph, what's my domain going to be for this graph now? Good, right? So this time we're only in the negatives. So we're going from negative infinity up to 0. And again, because there's vertical asymptote at 0, we're never going to get to 0, so we don't want to include 0. We're only including negative values this time for the x values. What about the range for this one? Good, right? Just like before, we're still going up towards positive infinity. We're still going down towards negative infinity. And so this is still going to give us negative infinity to positive infinity for the y values for the range. Any questions on any of the pieces of that one? Anybody need more time to get that? All right. Let's take a look at these. Okay, so we've got 2 plus the base 5 log of x. Okay, so what's our parent function going to be this time? Good, right? So it's going to be the base 5 log of x, right? So we'll make sure we keep the same base that we have here, but it's only going to be this piece. That's going to be the parent function. What's that graph going to look like? What are some key features of that graph? Okay, so 0, 2. So 0, 2 is actually on the y-axis, right? And if you think about it, all of our log functions, we're always going to have that vertical asymptote along the y-axis, right? So we're never actually going to cross the y-axis at all. Okay, so ignore the 2 here, right? Just think about this. The base 2 log of x and the base 5 log of x are going to look very, very similar. Again, the only difference between the two is that one's going to be a little bit steeper than the other. Okay, that's the only thing that's going to change. So if that's the case, where do we have an asymptote on this graph? Good. There's still going to be a vertical asymptote at x equals 0. Right? Just like the base 2 log of x, base 5 log of x still has that same asymptote. Where are we going to cross the x-axis? 1, 0, right? So that x-intercept has not changed. Base 2 log of x, base 5 log of x, it does not matter. We're still going to cross at 1, 0, right? So those are 2 key features of any log function. It does not matter what the base is. And again, the basic shape is going to be the same. The only difference this time is because of the 5, it's going to level out a little bit sooner than the 2 would, right? So the 2 is going to go up and to the right a little bit more. This one's going to go to the right more than it goes up, right? But it still has that same vertical asymptote. It's going to curve up like this, and it's just going to be a little bit shallower than the base 2 log. Again, basic shape is all we're looking for here, right? And that basic shape is going to be exactly the same as the base 2 log. Now, once we have the parent function, now let's think about our transformation over here. So what type of transformation are we going to have this time? Good. So this 2, it's a positive 2. This is going to shift up 2 units. Now let's think about the parent function and shifting it up 2 units. Right, so if I do that, what can we put on the new graph? Okay, so it will cross 1, 2. Good, right? So we had a point at 1, 0. That point's going to get shifted up 2 units. So now we're going to have a point at 1, 2 instead. So we know we got to go through that point. Good. What about any asymptotes this time? It's the same. Good, right? So shifting this graph up is not going to change where that vertical asymptote is. So we're still going to have a vertical asymptote at x equals 0, right? So we're still going to be approaching the y-axis here. We just need to make sure we're going through this point, which means we're going to cross the x-axis somewhere between 0 and 1 this time. It's going to come up like this, cross through. It's going to start leveling out as we go up and to the right. Okay. Any questions on the graph there? Okay, let's talk about domain and range. So what's the domain for that function going to be now? Good, right? So this is going to go from 0 to infinity. And again, we're not including the 0 because there is an asymptote there, but all of our x values are going to be in the positives. So we're going from 0 to positive infinity. What about the range for that graph? Good. Negative infinity to positive infinity. There are no restrictions on the y values here, right? So all of our y values are included. Any questions on any of those pieces? All right, now, what's our parent function for this next graph? Good, base 10 log of x, right? Now, if we think about the base 10 log of x, though, what's it going to look like? Yeah, it's going to look very, very similar to the base 5 log of x, right? So we can kind of go back and just think, okay, this is our parent function, right? We're going to have almost the exact same graph. We have the same vertical asymptote. We're still going through 1, 0. The only difference is base 10 log now is going to go out into the right even faster, okay, than the base 5 log of x would have, right? That's the only thing that's going to change. But this point and that asymptote do not change. So now let's think about if we were to graph this. Well, let's talk about the transformation first. What type of transformation do we have this time? Good. So this is going to shift to the right 3 units. Remember, if you have a addition or subtraction inside with the x, that's going to move it left or right. Because it's a minus this time, that's what's going to move it to the right. We're going back to this graph, and we're going to shift it to the right 3 units. So tell me something you know about the new graph. Okay, good, right? Close, so be careful. This graph here was at 1, 0, right? Shift it to the right 3 units, so it's actually going to cross at 4, 0. So 1, 2, 3, 4 now. So just make sure we're starting from the 1. We're going 3 units to the right. So now we want to cross the x-axis at 4, 0 instead. Okay. What else do we know? Good. The vertical asymptote now that was at x equals 0, that's also going to get shifted over to the right 3 units, right? So instead of being at 0 now, that vertical asymptote is going to be all the way over here at positive 3. Vertical asymptote of x equals 3 this time. Now, the basic shape doesn't change, right? So we're still going to go up and to the right through that point right there. Just that our asymptote is shifted all the way over to 3 this time. It's going to curve up to the right. And again, it's going to be a little bit more out to the right up compared to the base 5 log. Right? But in general, right, that's going to be our basic shape. Just make sure you have the correct asymptote and you go through the right x-intercept there. Any questions on how we got any of the pieces of that graph? All right, so let's get our domain and range now. So what's the domain for this new graph going to be? Good, right? So this time, right, we're starting from 3, we're going to infinity. And again, because there's an asymptote at 3, we're not including 3. So it's just going to be parentheses 3 to positive infinity. And then what's our range going to be? Good. Still negative infinity to positive infinity. Still no restrictions on the y values, right? So they're still going down to negative infinity, still going up towards positive infinity, right? So that's still going to be our range. So the main thing to notice here, right, the vertical shifts up or down, those are not going to affect your asymptote at all, right? That's still going to be x equals 0. It's only when we start shifting left and right that we're actually going to move that asymptote around, and that's going to affect your domain also. Okay, just keep that. Any questions on any of that now? Anybody need more time there? All right. All right, so here's our definition of a common logarithm. So any base 10 log is what we call a common log. And so instead of having to write the base 10 every time, we just write it as a log of x. So whenever you see log x just like this with no base, that is understood to be a base 10 log. Okay, so when you look at your calculator and you see that log key, right, it's just a log of x. That means it's a base 10 log or a common log. All right, so let's take a look at this. So it says we want to use the calculator to find an appropriate value for f of x equals log of x, and then use those values to sketch the graph. Okay, so we're just going to create a table kind of like we did for other ones, and then we're going to look at what the graph looks like. We should have at least an idea in this case of what this graph's going to look like. right, so what are some values that you would want to check here? Okay, 1, good, so let's check 1. So if I do f of 1, we're taking the common log of 1 this time. Well, what's the log of 1 going to give us? 0, right? Because regardless of what this base is, anything to the 0 power will give us 1. And so we know any log of 1 should always be equal to 0, right? So we've got that point, 1, 0. And we said that should be consistent for every logarithm, right? Regardless of what its base is. All right, what other values do you want to check? Three, okay. We're looking at log of 3. Now, in this case, remember, this is a common log, which means the base is 10. I don't know what 10 to some power is going to give me 3, right? I don't know how to find that exponent. But because we're using a common log, we can actually use our calculator now to at least get a decimal approximation of that, right? So on your calculator, actually find your log key and do the log of 3 and see what decimal value we get this time. Okay, 0.477. So 3, we have the decimal value 0.477. Okay. And in this case, right, we're just sketching a graph, right? So 3 decimal places is definitely enough because I'm probably going to put this really close to a half, right? It's going to be really close to 0.5. All right. What other values would you like to check? Five, okay. So f of 5. That's the log of 5. Again, this is 10 to some power gives us 5. There is no good answer there, right, that I can just figure out mentally, so I'm going to have to use my calculator. So what do we get when we take the log of 5 this time? Good, 0.699. And again, that's going to be really close to 0.7, right, when we go to sketch the graph. And so now we've got a point at 5, 0.699. What would be a value that I could figure out by hand without even needing my calculator? 10, right? Because if I find f of 10, I'm taking the common log of 10, which is a base 10 log of 10. What should that be equal to? 1, right? Because 10 to the first power would give me 10. And so now I'm going to have 1 as another point. Now, I think somebody might have suggested 0. Is 0 going to be defined on my graph? No, right? Okay, so keep in mind, right, we're still going to have that vertical asymptote at 0, just like we did for all of our other log functions, right? So we don't need to check 0. Same thing with negatives, right? No point in checking them, right, because they're all going to be undefined. Could we check some fractional values, though? So let's do that and see what we get. So give me a fractional or decimal value that I could check. Point, okay. Let's do f of 0.5. So we're looking at the common log of 0.5. Again, there's no good way to get there, right? Just doing it manually. So we're going to have to use the calculator. So what do we get when we do the log of 0.5? Good. So negative 0.301. Right. So it makes sense that we have a negative value because 10 to negative exponent would then give us that decimal value. Right. So we've got 0.5 and then -0.301. And so let's see if we can sketch this. And so like I said before, 0 is still going to be undefined. We're still going to have that vertical asymptote there. So x equals 0. We're still going to have the same basic shape that we had for all of our other log graphs. We're still going to go through the point 1, 0 here. That's our first point. But now let's actually plot some of these other points just to kind of see how this one is slightly different from some of the other ones that we've looked at. Well, I'm going to go ahead and do the decimal value here. So 0.5, -0.301. Well, if this is -1 here, at a half, we're just down a little bit, right? So somewhere in here. We know we're approaching the the y-axis here, x equals 0. So this is going to curve up. It's going to hit that point. It's going to go through that point. This is what the bottom part of my graph looks like. Now, if I go over to 3, I'm only at 0.477, okay, which is halfway to 1. I have a point right in here. Then when I get to 5, 4 and 5, I'm up slightly more, right, to close to 0.7. And it's not until I get all the way out to 10 that I finally get to 1. Okay. And so that's what I was saying earlier, right? As we increase this base, right, now we have a base 10 log for our common log. It actually goes up at a much slower rate than, say, like a base 2 log, right? Because a base 2 log, by the time you get to 2, you're already at 1, right? And by the time you get to 4, you're all the way up to 2. And so it's growing, base 2 log is growing faster than a base 10 log would, right? So base 10 goes out to the right at a much faster rate than it goes up in this case. But again, vertical asymptote doesn't change, x-intercept doesn't change, right? It's just how fast it's growing that's changing in this case. Again, if you can get things in terms of a base 10 log, then that at least allows us to put it in the calculator and we can actually calculate some values where some of our other logs, unless you have a newer calculator, right, that you can actually change that base. Most of the older calculators won't allow us to do anything other than that base 10 and one other type of log that we're going to look at. Any questions on that one? All right. Skip that. Natural log. So here is the other type of log that I want to talk about. So the natural log, okay, is going to actually use the natural base. So thinking back to section 4.2, when we talked about those natural exponential functions, those had a base of e. Well, now a natural logarithm is also going to have a base of e. Instead of having to write the base e log of x every time we want that as our base, though, we're just going to call it the natural log, and we're going to write it as ln of x, right? So that is an L, not an I. Okay, so this is ln of x, or natural log of x. So again, anytime you see this right here, just understand the base is an understood e that's not written. Okay, so we have to keep that in mind. Right, now some of our properties of the natural log, right, these are going to be very similar to the properties of any other log that we've looked at. So the natural log of 1 is going to be 0 because anything to the 0 power is going to give us 1, right? Doesn't matter what the base is. Natural log of e now is equal to 1 because, again, there's an understood e down here. E to the first power is equal to e. That's why this is equal to 1 now. Since this base, again, is e, and these match, right, these are both e's, this one should just give us whatever's in the exponent, so that's how we get the x. And then again, because this is an e and that base right there is an understood e, these are going to cancel out, and we're just going to get the x for that one right there. Again, no difference in any of these properties compared to the properties we've already looked at. We just have to understand that this base right here in e, and then all the properties that we've already looked at still apply. Would anybody like more time on that slide? All right. Let's take a look at these. We're going to find the natural log of e to the 8th power. All right, so thinking about those properties from the last slide, what should the natural log of e to the 8th give us? Good. All right, this is just going to be 8 because, again, the base of this is e. We have an e here. Those cancel out. Just give us the exponent. And so our answer is just going to be 8. Questions on that one? Okay. This one, we've got natural log of 1 over e squared. So what do you think we could do with this one? Is there a way I could rewrite this so that it looks like one of the properties we just saw? Good. Since we have an e squared in a denominator now, I could rewrite that as a negative exponent. So I'm going to call this natural log of e to the negative 2 power now. Because e to the negative 2 would be the same thing as 1 over e squared. Well, now, if I'm taking the natural log of e to the negative 2 power, what should that be equal to? Good. Just what's in the exponent. So this is just going to be equal to negative 2. Any questions on that one? All right, now the last one here, we've got natural log of 5. So what this is saying is e to what power is equal to 5? So is there an easy way to find that value that we would put over here to do e to some power gives us 5? Or does this look like any of the properties we just saw on the last slide? Okay, so it wouldn't be 1, right? Because if we wanted a 1 here, then that would be e to some power is equal to e, right? Because e to the first would be equal to e. We don't have an e in here, we have a 5 in here this time. Okay, that would be e to the 5th equals 5, which again is not true, right? Because e to the 5th, e is like 2.7 something, so that to the 5th power would not be equal to 5. Okay, e to the 0 power would be equal to 1, right? Because anything to the 0 would be 1, and that's not equal to 5 either. So can we make this look like any of those properties that we just looked at on the last slide? Okay, good. Your silence is a good thing because no, we cannot. Right? So there is no way to use the properties from the last slide to solve this because I can't figure out what e to some power is going to give me 5. So this is where we would pull out our calculators now and we would get a decimal just like we did with those common logs. So we actually do have a key on our calculator to do the natural log. So take a look. On my calculator, it's right under the log key. So on the left-hand side, on most of the TI graphing calculators, that's where it's going to be located. But again, if you can't find it, right, let me know. But all science and graphing calculators should have a natural log. So we're going to do natural log of 5. We're going to get a decimal, round it to 3 decimal places, so 1.609. That looks good. Okay, so whenever you cannot apply your properties, right, there is no way to make it look like anything we've done up here. All we can do is just put that in the calculator and get a decimal value this time. Any questions on that one now? All right. I'm not going to rush through this one, so we'll stop there. Okay, so we'll start with this example tomorrow. Again, the homework has been moved to Tuesday, and hopefully I'll have all the tests graded by this afternoon, so keep a check if you want to see your grade. It should be in there no later than this. Okay, any questions before we go today? All right, well, have a good afternoon, and I will see you tomorrow.